Okay, in this recording, I am using the code agc_compare_homework.m to explore the two adaptive gain control algorithms that we had talked about in class. And I want you to use the same code and play around with the parameters and actually hit the run button yourself and notice the effect that different changes have on the overall results. Okay, so the first thing I'm going to do is walk you through how to use this code. I've got everything programmed for you so that you can look at the top of the code and switch between different cases. So for example, if I make the envelope flag equal 1, we get this kind of sinusoidal type of fade where, you know, the amplitude of the received signal is growing and then it shrinks down and then it comes back up, and I made it with a sinusoid type function to give that shape. Alright, if you flip this to a 2, you get a step change in the envelope. So it's interesting to then note what happens to the gain parameter, so that's the upper curve here, when you have a step change in the envelope size. And this is the output signal that's generated from the adaptive algorithm. And then down here you have the soft decision diagram, which this is producing, relatively correct soft decisions because these are properly decoded as 3s. Greens are 3s, yellows are 1s, blues are -1s, and reds are -3s. Okay, so you can also look at two different algorithms. Algorithm number one is the adaptive algorithm that we discussed a little bit in class. We didn't actually derive the equation for it, but we talked about it a little bit. And that's the one that uses basically a certain power that you're trying to hit with the adaptive signal, and the adaptation makes adjustments to hit that power. Okay, so we'll go down and look at the code for that in just a second. But first, if you switch this to a 2, the 2 is an algorithm that uses that approach that we talked about in class, where I'm trying to match the peak amplitude, all right, or the maximum amplitude. So when I run this, I've switched algorithms, and this looks sort of okay as working, except for these spikes. And you go down here to the soft decision diagram. These spikes are actually going to cause problems when you try to decode these soft decisions into making a final decision about whether a 3 was sent, for example, or a -3. Right in here, it's kind of hard to tell. I'm sorry, not 3 or -3. In this case, it would be 3 or a 1. So in here, it's kind of fuzzy because there's a spike there. Well, I guess it'd be expected. That's where the transition occurs. More in here, where clearly the envelope of the signal was correct, but the adaptive algorithm generated some weird effects there because it's not tuned very well. Okay, so that's the next thing I want you to do, is play around with how you would tune this to produce what would be better results, and to know what better results look like when you see them. Okay, so if I change this, one idea might be maybe I'm adapting too fast, so let's go, instead of 0.001, let's do 0.0001. Okay, so when I rerun that, yeah, I see a much smoother curve here for the adaptive gain parameter. I see much smoother results with the symbols, soft decisions. All that looks good. The expense I paid there was, it's a little longer of a transition width to go between the correction factor here. There's no correction factor needed, but when I had this step fade, the step faded down to, I took the amplitude and multiplied by 0.3. 1 over 0.3 gives me the corrected value of the gain. And so it gets up there. It does the right thing. It just takes a little while to get there with 0.01. So, if I'm tuning this up, I might think, well, let's go a little bit faster and see if we can get it to work. And that's still too fast because now I'm getting these spikes again. Okay, but then my thought process is, well, maybe it's because the buffer that I'm averaging over, it needs more time to pick up on some peaks. All right, because this algorithm depends on locking in on values of 3s and -3s, and if there's not enough of those that show up in the window, it might cause this algorithm to either spike down, or if there's too many of them, it might spike up. All right, so if I had a larger window, it would reflect more of what happens on average. So if I bump this up to say 300, so I'm looking at a window of 300 samples to base my algorithm on for my maximum algorithm. And so when I move that up to 300 samples, yeah, it looks like indeed we cleared that up. All right, and so we were able to get a faster convergence and not have these weird spiky things happen in the gain parameter. Okay, so I'd like you to understand that and play around with that. Okay, let's go down into the code a little bit. I realized when you look at this, it's like, wow, look at all that code. And if you zero in on any given section, I'm sure you could figure that out. But what I wanted to do is get to the part that matters. All right, so the part that matters is the adaptation step. All right, so remember what we're trying to do here. We're trying to adjust the gain, the amplitude of the received signal, so that it falls along the right scale. All right, so the first step on that is simply you take the new signal value that you're trying to produce and you multiply by the gain parameter, A of k. This is sample by sample, because k goes from 1 out to the number of samples that we have. Okay, so we form S of k. All right, then I have some test logic, and that's just to generate cases easily. So we're in case 2, where I'm looking at making this buffer of signal values. So I take S of k and I square it. All right, and so my idea on this algorithm is I'm looking for the maximum values here. So the maximum value of a perfect waveform would either be 3 for the plus case, or the maximum negative value would be -3. So when I square that, I get 9. So I'm stuffing these into this vector, or this buffer, all right, and keeping track of all those values. Then I look at the maximum value in that buffer and return that to max val, and then my adaptation is simply max val minus 9. All right, so if my amplitude in the max val vector is too big, say I got a 9.5, 9.5 minus 9, that's a 0.5, then I multiply by mu, and I adjust my gain down a little bit to say, oh, that's a little too much amplitude, so let's adjust things down. All right, so as we go through this, every sample, we get a little closer, hopefully, to the real answer. Of course, the real answer might be time varying, so we're hoping to track those kind of changes. All right, so this is looking pretty good for a step change in the parameter. So you might then say, all right, well, what happens if you have sort of a more slowly varying case of a fade? All right, so that's why I looked at this sinusoidal type fade. So we put a 1 here, use the same parameters, run this, and again, it looks like we get pretty good results, right? Because here's the fade, this is the shape of the input signal that we get, all right? And this is the gain parameter that, there's an initial convergence problem here. It started with an initial value of 1, so it has to zoom up there to get corrected for this fade in the signal when it first starts. All right, so there's a transition there, but then it starts tracking it pretty well. Okay, this is a pretty quick change. It's not a step change, but there's still a little bit of a change, and so you see there's a transition region that happens right in here on the output signal, and that gets reflected into the soft decision diagram. Okay, so I want you to play around with that. Here's an interesting thing that you can try to do. You can try to break this. What if I take a lot of samples? That doesn't seem to break the max algorithm, if you take too few, what's going to happen? So if I took only 10, it's not broken, but it's definitely got a lot of noise jitter in the amplitude that shows up in the S of K that actually gets reflected into the soft decision diagram. So that wouldn't be as good. This looks like random noise, but yet there's no random noise turned on in this example. Okay, so you think, well, maybe if I slow down my adaptation size, that would work to fix it. Okay, it helps, but there's still this transition region that seems to get worse whenever we decrease that averaging length. All right, so for this algorithm, the averaging length seems to matter. So if I put this back up to 300, I get much cleaner kinds of results. Okay. Another thing I wanted to do, let's go back to the first algorithm, because that's the one ultimately we're going to use the most. We'll talk in class again about why the J-max algorithm might not work for certain signals. For these two signals it works, for this signal it works, but there are cases where it's not going to work as well. We'll get to those. All right, so we're going back to the first algorithm, the power matching algorithm. All right, let's look at changing the initial condition here. Well, let's run it with a 1 as an initial condition, and we see, yeah, that's producing a reasonable result. Okay, there's a little bit of it's really not correcting the amplitude all that well. It's not adapting fast enough to keep track of those changes. So I would need to fix that. So let's change this adaptation rate. Let's bump it up by a factor of 10. That's a little bit better, but maybe there's too much averaging. Not much change on that. So let's adapt even faster, see what happens. Okay, now it's adapting too fast, so maybe 0.05 would be good. Okay, and now we're getting something that looks like it's more constant amplitude, although there's still a lot of jitter in that particular algorithm. So increase the averaging time a bit. See if that helps. When you play around with this particular algorithm, the update size does a pretty good job of averaging in and of itself. So changing this averaging length doesn't seem to do much. Okay, so maybe you get a little more jitter-like stuff showing up in the gain, but you could correct for that by simply making a smaller mu value. Okay, so I think, if you made soft decisions on this self-decision diagram, these have enough spread on them that you'd likely not generate very many errors during the transition where it goes from a fade down to a fade back up. Okay, so play around with that. The only thing that changed in the code on these algorithms was you take this vector that you're averaging into, all right, and you replace the first vector with the adaptation derivative, right? The thing we derived, all right? So this one comes from the book. We didn't actually derive it in class, but if you use the JN algorithm from the class, this is the formula that comes back out of that. You place that into the first value of the buffer, and then for each sample you slide things over to keep the most current value of the update equation in the first position in the buffer. Okay, then the new gain is equal to the old gain minus mu times the average of AVEC. All right, so these few lines of code are the only thing that need to change if you change the adaptive algorithm. All right, so down here, when I use JMyMax, I'm using a similar type of approach where I have this buffer, but in the buffer, I'm just looking at S of k squared, all right? And my adaptation is really going to depend on, I look at everything that shows up in this buffer, all right? So view this buffer as a collection of all the most recent S squared values, all right? Most recent meaning the length of the buffer, all right? Take the maximum out of there and make that adjustment, and you have the new update equation that shows up for the second algorithm. Okay, so there you have it. Hopefully you can think through this, run this yourself, play around with it, and your goal here is to get an idea of how to make good results show up on the figures and to recognize them when you see them. Oh, and I thought of one more thing I wanted to show you. This code also has a way to change the initial condition. So look what happens when we start with an initial value of -1 and rerun the code for the sinusoidal fade. This would also happen with the step fade, I think, but we'll run that in a second. But the -1, the initial push is to have the algorithm converge to negative values of A. All right. So we've talked about that it's, there's an error surface that's created and the initialization matters. Okay. So in this particular case, A converges to a negative value. And what I want you to notice is these flip. All right. So the green is usually on the top, and now it's going to be the reds that are on the top because the 3's turn into -3's and vice versa. Okay, so when this had this problem of converging in the wrong direction, we got essentially an inversion of the waveform. We're going to find out later that it's possible to detect when something like this happens and make the correction, because after all, it's just changing the sign of the signal. But you should be aware that that can happen. All right, so you might say, well, why don't we just start at 0? If you start at 0, there's no telling which way it's going to go. So if I started at 0, it still converged to a negative value. We could change the envelope to see if that makes any difference. Nope, it still converged to a negative value. If you cheat it up a little bit to maybe 0.2, okay, yeah, now it's going back to positive values of A, like we would expect, and there's no longer that sign inversion that shows up in the symbol diagram. All right, so wanted to point that out to you as well.